So the importance of precision detection, I think this is very important. We have a couple of reasons. Firstly, we want to test the standard model. So many experiments aims to test the standard model with the extreme accuracy. So this is a very strong need. And also the parameter determinations also need precision. So because properties of particles like mass, charge, lifetime are determined through data analysis, and higher detector precisions actually reduce uncertainties. This is very important. And also some experiments actually has got the background issues. So how to suppress background. We also need precision detection, and also search for rare process and signals, because new particles and physical phenomena frequently emerge through rare processes. Without high precision, actually, this kind of subtle effects will be lost in the noise. So then, introduction about the role of the detectors. Sorry. Okay. This figure is from the Sun website. Is taking a close look at the HC. So when we look at this figure, this is type of particles, and this is a type of these are different subdetectors. So different types of particles go through the detector through to some depth. So and for example, the photons can only be recorded by electricity ecal, and the electrons will be recorded by also tracking detectors and also ecal, and the muon will go through the whole detectors, and other particles like hadrons will stop in the hadronic calorimeters, and for neutron hadrons actually only be captured by a hadronic calorimeter, and neutrinos actually go through the whole detectors. So this is in this figure we can find. So normally we use a vertex. We need a vertex detection, detects the primary interactions point, and identifies decay vertex for the short-lived particles. And also we need tracking, measure the charge particles path to determine the momentum and the charge. And we need the calorimetry to detect and absorb particles to measure their energies. And this is also very important. And the muon detections identify the penetrate muons, and then we'll separate them from other hadrons. And time of flight is also very important, and some experiments, the precision timing is also very important to distinguish the overlapping events. So then how many interactions between particles and matter? I think I just list all the interactions here. There are ionization and excitation, and Planck-Choron, and pair productions, Compton scattering, and photoelectric effect, hadronic interactions, and Cherenkov flight, and neutron and neutrino interactions. I think Liang Jian already covered this part, because for Juno experiment we use water pool to detect the Cherenkov light from the muons, and also neutrino interactions. We use the scintillate large, very big liquid scintillate detector to detect neutrino from nuclear reactor. So, and actually these interactions, physicists make use of these interactions to build the detectors. So I think this is very important. And also, Tao Lin talked about simulation. So in the Jiang-4 simulations, actually the Jiang-4 will simulate the particles interactions with matter. So all these interactions has been included in the Jiang-4 simulation. So how about the detector performance? So basic detector performance, we are thinking about very important. One is the resolution. So the detector should be able to precisely measure a physics quantity like position, energy, or time. And another factor is very important in efficiency. So the detector should correctly register the particles and interactions when it pass through. So the probability should be high. Ideally, it should be 100%, but it's very difficult to achieve this kind of efficiency. So I think I just give a very brief, big picture of the detectors and how to implement it. I just want to use the BESIII detector as an example. So BESIII experiment located at the Beijing Electron-Positron Collider, actually operated by IHEP in Beijing. So the energy range it's at the center of mass energy between 2.0 GeV and 4.9. So it's not very high energy, but it's ideal for studying charm quark physics. So the physics of this experiment is to investigate the properties of particles like charmonium, light hadrons, exotic states search, such as tensor quark and global. So we also have colleagues from Russia. Say here, the JNR and BIMP and Liberty Physical Institute, they are members of BESIII collaborations. So from this figure, we can see the LINAC, and this is the ring, storage ring, and BESIII detector actually locates at this point. So this is a photo of BESIII detectors. And the collaboration actually has got many members. 83 institutes from 16 countries, and total members about 600. So they publish lots of papers, so about more than 500 publications since the detector starts data taking. So this is statistics is the year before last year. So when we look at the BESIII detector, its detector is a cylindrical and covers about 93% of the whole solid angle. This coverage actually allows to capture a wide range of particle interactions. So from inside, this is the major chambers, measure the momentum and trajectories of charged particles, and offers excellent spatial resolution. It's inside, most inside. And also then outside a little bit is a time flight made of plastic scintillators. Helps to identify particles by measuring their flight time. And then it's electric magnetic calorimeter, we call it EMC, and measure the energy of photons and the electrons. Has a barrel and end cap, and most outside it's a muon counter. Actually use the RPC to detect muons. So it's quite simple. I also look at the project on the NICA machine. It's called PSD, right? It's very similar. Looks like very similar. So then for the major chambers, it's a multi-layer small cell design. and use the helium-based gas mixture. And the length is about 2.6 meter long. And you can, this is the Y's, and this is the plots for the MDC. And I think this also shows the structure of the MDC. So the Y, there are two types of Y. One is sense Y's and another fuse Y's. So the cell, we look at the cell geometry. The field Y, the sense Y is surrounded by the field Y's. So this we call the cell, drift chamber cell. So look at the size is about 1.2. It's actually 12 and to 16 millimeter. It's a small size. And the inner has got most inner. There are 8 layers, and the outer is about 35 layers in the outer chambers. So we have a different type, stellar and axial layer Y's, and with a different, for stellar Y's has got different stellar angle. I just put them in this table. So the physics interaction, in the drift chambers, when a charged particle passes through the MDC cell, it ionizes the gas and knocking the electrons free from gas atom and creates an ion pair. So then, the electron will drift towards the sense Y. So as the electrons approach the NY, the electrons gain enough energy and will cause secondary ionizations, triggering, we call it electron avalanche. So this is a figure shows the drift time versus drift distance. We call it XT relationship. So the X for drift distance and T for drift time. So by using this XT relationship, actually we can measure the drift time to the drift distance. So then by collecting lots of signals from many Y's across many layers, then drift chambers actually can construct a 3-dimensional trajectory of the particles. So this is the basic idea how the drift chambers can be used to measure the momentum and the trajectory of charged particles, then measure the momentum. For charged particles, then the beta block equations governs the energy loss. So because what I talk about this energy loss, because we also use energy loss to do the particle identification. But in practice, actually we are using empirical models instead of the beta block equation. So we build a model, use real detector data, because this can be more accurate, and this method is data-driven. The equation we use is as following. So it's quite complicated. Here there are 5 parameters, P1 to P5, and the Y is the beta gamma. So we just use the control examples like protons and kaons and pions, muons, and electrons to build this, to extract these parameters, P2 to P5. Then we have these models, and then we use this model to do the particle identifications. So in order to obtain this curve, beta gamma curve, so calibration is very important, because it ensures the energy loss measurement are accurate, consistent, and across different detector conditions, because the detector's performance actually changes with the detector conditions. Then how we do the calibrations. So the calibration consists of two levels. One is the hit level corrections, another is track level corrections. So for hit level corrections, we just apply, this is applied to individual measurement actually from each cell. So we do path length corrections to adjust the actual distance particle travel through the drift cell. And we also do the gain normalization, correct for the violations in the gas gain across different cells. And we also do the Data. Data means the distance of closest approach. I think this is the cell, and this is Data. We also do the Data and the entrance angle. This is the entrance angle. It's here. Corrections. This account for how the particle enters the cell, which will affect the ionizations. At the track level corrections, this is applied to the average DDX over the hits in a track. So the most important correction we do is called space charge effects. So we do the corrections to compensate for the local electric field distortions due to the accumulated charge. Because I already mentioned the avalanche. So when the avalanche happens, it will cause this kind of distortion. So we do the corrections, then make sure we obtain the unified DDX measurement. Then this can be used to do the particle identification. Then the second detector is the time of flight. So the time of flight is based on plastic scintillator bars read out by PMT tubes. The PMT tubes is just at the ends of the plastic bars. So the solid angle coverage for bellow is this number, cosine theta less than 0.83. And then for the end cap is cosine theta is between this region. So for the bellow, have two layers, and totally there are 88 scintillator bars, this kind of scintillator bars. And for the end cap, we have each end cap consists of 48, and it's actually shaped like a fan. And this is the end cap scintillator. So the physics interactions in TOF, it's quite simple. Basically, the ionization and excitations. So when a charged particle passes through the scintillator, it interacts with the atoms via Coulomb force and causing electrons to be excited and analyzed. So then the scintillation. So these excited atoms or molecules return to its ground state by emitting photons. So it's very simple. So the very important is how to detect photon effectively. I think for Juno experiment, this is also the same. Just use a PMT. For Juno, we have used a very big PMTs, 20-inch PMTs. And also for Juno experiments, these are large coverage, and the detector is very big. So we use around 20,000 PMTs to do this work. So, but for BESIII, it's relatively easier. So then particle identification with TOF, because TOF detectors measure the time the particle takes to travel between the interaction point and the detection point. So we got this distance actually can be measured by drift chambers. And we have this distance and we have the time. Then we can get the information about the particles' mass, can be inferred, and then can help to distinguish between the particles like pions, kaons, and protons. So this figure shows the time difference of k and pi versus cosine theta for different momentum from 0.6 to 1 GeV. So for BESIII, if we use two layer, then this 3 sigma separations is here. Above this line, we can do the 3 sigma separations. If we use one layer, is this line. So above this line, we can do 3 sigma separations. So then we look at the efficiency. This is efficiency versus momentum. So this is efficiency. We identify K. We just identify kaons from kaons. So this is very high. And this is we misidentified the kaons from pions. So actually the ratio is we hope it can be lower, but when the momentum goes high, and the fake rate actually goes up, so and the efficiency goes down. So then I come to the BESIII ECAL, we call EMC. It's made of CSI crystal pyramid crystals. So it has the bellow and cap 2 parts. So for the bellow, we have about 5,280 crystals, and for the end cap, we have 960 crystals. So this is the design performance. So the energy is between 20 MeV to 2 GeV. It's very big, and the energy resolution up to 2.5% for at 1 GeV, and the time resolution. I just put the performance here, so we will check if we meet the performance requirement by doing the reconstruction and do the performance studies. I will compare with this performance requirement later. So the physics interactions in EMC, it's basically the scintillation mechanism. When a high energy particles enters crystals, it deposits energy, and it excites the crystal lattice, and the energy is then released through the visible light we call scintillation. So, and what I want to also mention is that the crystal actually also doped with a very small amount of cerium. So actually the cerium acts as an activator, which will enhance the light output and shift the emission spectrum to match the sensitivity of PMTs. So for Juno experiment, we have a similar idea to do this kind of try to improve enhance the light output. And then for the decay time, because CSI actually has a very slow decay times, about 1 microsecond. This affects the timing resolutions, but because for BESIII experiment, the timing resolution is not so important. So by using this very big time windows, we can improve the energy resolutions. And then for the measurements, actually, it consists of 2 parts. One is a cluster formation, basically grouping the adjacent crystals. This crystal has energy deposits, and we identify them as clusters, and actually and do for the reconstruction by using after this clustering, we can get the energy and the position of the clusters I will talk about a little bit later about the reconstruction in EMC. So the most outermost detector is a muon counter, MUC. So the main function is to separate muons from charged particles, charged pions, and other hadrons and other backgrounds. So it consists of RPC inserted in the steel plates. This actually also works as a magnetic flux return yoke for the solenoid magnet. So for bellow, there are 9 layers of RPC, and for the end cap, this part, we have 8 layers of counters in the end caps. So the reconstruction, we just extrapolate the track in the measured by the drift chambers to this MUC and associate the foiled strips of in the MUC with the extrapolated track, and then we can do when we do the tracking, then we can do the muon identification based on track parameters and hit patterns. So I already talked about the detectors. So how to do reconstruction and get the measurements. We are using a software method. So that's why I also want to introduce how the software framework works and just a little bit. So the software framework. So what's a software framework in HAP? So actually, it provides the structure for handling all stages of data processing, including simulation, reconstruction, calibration, and data analysis. So why it's important for experiment? Because software framework is something like a central nerve system of the experiment, because it connects everything and keeps it functioning smoothly. So what's the requirement? What are the requirements for a framework? One of the most important thing is scalability, because future experiments will produce multi exabyte data sets. So the framework actually help manage this kind of this scale efficiently. So scalability is very important. So another factor is modularity, because for collaboration we have lots of members and lots of teams. So different teams can develop components independently. For example, the tracking particle ID, they can work separately, independently, and finally put them together into the framework. So the modularity is very important, and another thing is the flexibility. So because we also should allow swapping out sub-detectors and algorithms without writing everything. So this is we call the flexibility. And the maintainability. So the common software frameworks like Gaudi, Key for HAP, and for Juno we have a Sniper, actually reduce the duplications, make a long-term maintenance easier. So this is the reason why we need a very good framework. And also the performance, because optimize frameworks support parallel computing, GPUs, AI, and machine learning integrations to speed up the processing of data. So all these factors are very important for a framework. So then we'll talk about the Gaudi. What's Gaudi? Gaudi is a modular framework designed to support the development of data processing applications in high-energy physics experiments. It was originally developed by LHCb experiment at CERN, and has been adopted by many experiments, other collaborations like Atlas, GLAST, HAP, and here also the BESIII. BESIII. BESIII also use Gaudi as its a framework. And also the future CPC experiments, they also use Gaudi. So for the future experiments, there's a project called T4HAP actually developed the common software stack for future experiments like CPC, FCC, CLIC, and IOC. So the core concept of Gaudi, I think is one thing is a component-based design. So the Gaudi is built around the components with well-defined interfaces, allowing physicists to plug in algorithms, services, and tools as needed. So this framework can be support full train of HAP data workflows from simulation to reconstruction and to analysis and visualization. So when we look at the architecture of the Gaudi, one feature is very important is separate of concerns. So there are two aspects. One is separate algorithm from data objects. So the data objects represent hits, tracks, and other physics entities. And another thing is separate transient data from persistent data. So what's transient data here? Transient data means data objects in the memory, and the persistent data is the data stored in the file or database we call it. So there's a very clear separation between the transient objects and the persistent data. So this is the two features. So and then another thing that the architecture is data centered. So this is the data, and this is the algorithms. So algorithms communicate with the transient data store and minimizing the coupling. This part, data part, and this is the algorithms. So for the physicists, the most work they are working on is developed algorithms and services. So I will say a few more words on algorithms. So this is a figure shows a concrete algorithms implementations. So it implements two abstract interface, algorithm, interface of property, and also these algorithms use lots of services through the interface. So, and the services actually, the algorithm communicates with these services through the interface, not directly. Why it works like that, I will, in my next slide, I will talk about this. So by this actually, the basic idea is helps to reduce the tight connections between the softwares and making it easier to swamp between different implementations without changing the algorithm itself, because it's user interface. So if the interface is not changed, then nothing needs to be done to the algorithms if the services has been implementation of services has been changed. So this is the coupling. I think we just decouple these implementations. This is very important. So I will further show an example how to decouple things. This is a simplified version of interface. Here, its name is my interface, and in this file defines functions. It doesn't have any code. We call the abstract method. It's called do something. It's equals 0. So basically, it's the abstract function. So and this method acts as a contract. So whoever uses this interface doesn't need to know the detailed implementations. It just includes the head files and then use it. So how to use it in algorithms? This is the example code. So when a special function called SVC, here I think somewhere is SVC, and this actually finds the service named my service provider. This is a concrete implementation of a service. So by using this SVC, it gets a pointer to this service. Then the algorithm will use this pointer do something. And another very important algorithm actually doesn't need to clean up or delete this service. This kind of work will be managed by the framework. So by using this kind of interface technology, so the algorithms can be very easily to call a service and do something without knowing the details of the implementations. So this is just examples how we implement this interface technology in our programming. Okay, so I will also say a few words about event data model. So because we already give you a big pictures of the framework, then another thing is important is the event data model, how we describe the detector data. There is a software called EDM for HAP. Actually, it's a genetic event data model designed for HAP Collider experiments. So in this EDM for HAP, it's actually described the event data in different data processing stage. For Monte Carlo, they also have like a same track hit and the same calorimeter hit to describe the data generated by Monte Carlo. And also raw data. So this data is from Detector. So they have the event data model for raw data, and also for the results from Monte Carlo digitalization, they also provide the event data model for this data, and also for after reconstruction and the input of analysis, they also provide event data model. So EDM-FAP actually supports multiple back-end data formats. So both root and LCIO data formats are supported. And also event data model, EDM-FAP, we can extend it to meet a specific requirements of a given experiment. How to extend the EDM-FAP? We just follow a few steps. Firstly, define the new data types, and also implemented the serial for the new data types, and integrate with the root, and register new classes with the root, reflection systems, enable I/O support. So we just follow these 3 steps. We can add new class into the event data model EDM-FAP. So then we look at the details about the event data model. I just give you a few examples. Here is a track hit and a track. So the track hit is the input of reconstruction, and the track is the output of reconstruction algorithms. So we look closely at what we have for the track hit. So basically we have the sensor ID, which this sensor creates this hit, and also the time of the hit, and also the energy deposit on this hit by this hit, and the position. So I think this is the key features of the track hit. Then how about the track? The output of reconstruction, the track, we have a chi-squared of the track fit, because for the track, we find a track, we will do the fitting. So the chi-square is very important. And also other features like track states. This is actually the real track parameters. We call track states. And also because the track can be constructed by other tracks. So this is also possible, so can have the daughter tracks. And also these tracks normally consists of track heat. So this is a vector of track heats. This heat has been used to create the track. So when we look at the details, seems like it's not difficult. It's reasonable. Actually meets what we are thinking about, how the track heat look like and how the track look like. And for the calorimeter, they have very similarly. They have the calorimeter heat. Similarly, it has a cell ID, energy of the heat, and the error of the heat energy and time, and also the position of the heat. Actually, this is in the global coordinates. So for the cluster, this is the output of EMC reconstructions, calorimeter reconstructions. So there's the energy of the clusters, position of the clusters, and the direction, the polar angle, azimuthal angle, and also the clusters, the heats which contribute to the clusters, and also this cluster can be consists of daughter clusters. So these features is basically for the event model of the calorimetry. Then how about reconstructed results, reconstructed particles? What we have for reconstructed particles? So here you can see we have the PDG ID. So this I think stands for the type of the particles, and also energy of reconstructed particle energy, and particle momentum, the charge, the mass of the reconstructed particles, and the decay vertex of the particles, and the clusters that has been used for these particles, and tracks have been used by these particles. I just put these features here. Okay, then I already talked about the event model for tracking, for a tracker, and also for a calorimeter. So then how to retrieve the data, because we can retrieve the data inside the framework. So the algorithms want to retrieve the data, he will send a request to the data service. Then the data service will look at the data store. If the data appears in the data store, it will return it to the algorithms. If it doesn't appear in the data store, then the data loading will be triggered. So then it will use the persistent service, then we'll call the proper conversion service, and because conversion service consists of several converters, we'll select the proper converters and then find the data in the file, and then create the objects, and then register into the data stores, and return the pointer back to the algorithms. So the algorithms request data just send a very simple request. It triggered lots of actions, but all these steps actually was controlled and was done by the framework. So these very complicated steps actually is a work of responsibility of the framework. So the algorithm doesn't need to know anything. He just requests the data, using the path. So then it will get the data the algorithm needed. So it's by using the framework, this process will be very simple for the algorithms. Okay, then we have the detectors. We also have the software framework. Then how to do the reconstruction. I also use BESIII as an example. So firstly, if we want to do reconstruction, we need geometries. So for simulation, Lintal already talked about simulation. It needs the geometry. For reconstruction, we also need geometry as well. And other applications like visualization, it also needs geometries. So then different applications, all of them need geometries. So the geometry management is very important. So by using the proper service, can manage the geometry properly and create the geometries for different applications and from the same source. So this is very important. So actually, for BESIII Experiment, they are using GDML. This GDML was developed by John 4 team, and the BESIII actually extend this schema a little bit, and also create a root schema. So for both will be used to support the management of geometry. So then this is a figure shows for the geometries and the materials from the single source, very likely from the files, and then use XML written in XML descriptions, and then using different schemas, create different data, geometry data for different applications. So, but what I'm talking about is ideal geometries, but in the real life, actually, there are another problems. We call it alignment, because alignment is a very common problems for different experiments. So this is caused by mechanical imperfection. So because we assemble the detectors, and this kind of detector assembly will cause misalignment. For example, the wires and other components. So basically, the geometry will be not ideal. So we will use the data to get this kind of misalignment parameters, and then we will create another more realistic geometries, and this can be used by simulation and reconstructions. And how to do alignment? I just give you a very simple examples how to do alignment for the drift chambers. So for the drift chambers, I already mentioned. So there, according to the geometries, actually there are 16 independent components in total. So listed here. So then for each component, there are 3 alignment parameters. We called delta x, delta y, delta z. So actually, lots of parameters we need to extract it from data, and how to do that. So for BESIII, we use 2 methods. One called residual method. We use the cosmic ray tracks to estimate this kind of very big displacements. So residual will be plot as a function of phi. And then the misalignements will be inferred from these patterns. And another method we call millipede matrix method. This is a global least squares fitting techniques. Simultaneous fit the alignment and track parameters across many events, and handles large amount of parameters like translations, rotations for each detector component. And both methods actually have been used by BESIII Experiment to do this alignment. So then just here, just a very quick how to do the alignment. So this is a cosmic track. We're using we called tracking algorithm. We call MDC Petarack algorithms. So actually, for the larger end plates, because drift chambers there are two big large end plates. Actually are positioning according to the mechanical measurements. This is what was done at the start of the detector installation, detector installation. And the cosmic tracks actually will be fitted, and actually we just using the outer sections, and then we will align the inner and also stepper, the inner part. And we look at the results before alignment. We can see this is the residue and this is the file. So it looks like this. And after alignment, so all the this kind of distortion disappears. We have a very good residues versus file. Right, so then after we finish the alignment, then we can do the reconstruction. So how to do reconstruction, how to do the tracking, we have basically different algorithms for this purpose. One is called Petarack. We use a template and matching to firstly find the track segments in the super layers. What's super layers? Super layers consist of 4 layers. So this super we call super layer, and then we link the segments together and fit the track and get the track parameters. This is one method. Another we call the TSF method. We just apply conformal transformation to convert a circle, because the track in XY plane is a circular into the straight lines, and then find the common tangents to the drift circles, to the identify track segments, and then finally we do the fitting. This method actually is effective to the lower PT track finding. So I think I won't go through the details. I put all the details for track finding here. I just keep this Petarack. I already introduced the ideas. So I just want to show you the patterns. What's the patterns? So for the super layer, there are 4 MDC layers. So we have this kind of patterns. So we call it 4 hit patterns. Totally, we have, for example, for this, we have 8. So we can also construct 3 hit patterns similarly. Then by using these patterns and connect the segments, then we get the tracks. So for the conformal transformation method, what we do, because we do, as I mentioned, that we do the conformal transformation. So this is a position in XY plane. We do the transfer to another plane, another space, using this cushion. So I think a circular will finally get the straight line, which will be transferred into a straight line, a line. So this XCYC actually is the center of the circle. So for the circle in XY plane will be transformed into a line, but for a circle doesn't pass a region, actually will keep as a circle, a new circle. Doesn't pass through the origin, will keep the new circle here. Here I will see now the track finding will be transferred to something like that. So we have this is corresponding to the hits. Then we will find the line. So there are several possibilities. Finally, we find the line, and this is the hits. Then we will do, when we finish the pattern recognitions, then we will apply the track fitting and get track parameters. So when we complete the track finding, then we will get the track parameters we need to the Kalman filter. So traditionally, the track finding and track fitting, they are two separate steps. So for BESIII, we just using the traditional method. Then for the next stage, we just apply the Kalman filter to do the track fitting. Because I will talk about Kalman filter later, so I won't go talk about details about how to do track fitting here, because the principle actually is the same. So finally, we get the track parameters for different hypotheses, like electron, muon, pions, and kaon, and protons. So the user algorithms can choose these parameters according to the data type, the particle ID. Right, so the Kalman filter also need to handle other effects, material effects, and also non-magnetic field, this kind of effects. So the material effect is a very important thing that the Kalman filter need to handle. So for charged particles move through detector materials, so they scattered due to the interactions with the atoms and the Kalman filters, and will account for this. Basically, just adding some process noise to the state update, modeling the uncertainties introduced by scattering, and improve the momentum resolutions, especially for the low energy track. So this is an example before fitting for the 0.3 GeV charged particles. You see the peak is here, is lower. Then after fitting, it's exactly the same, is at the 0.3 GeV. So non-uniform magnetic field is another thing a Kalman filter need to do. So the Kalman filter needs a magnetic field map. When he has a map, then he can handle this. I won't go through the details. Here I just show you the results before the fitting. So for 1 GeV charged particles, it's actually the momentum is higher. There are some bias, and after fitting, there are no bias. Right. So then we look at the reconstruction performance for the tracking efficiency. How to define the tracking efficiencies? We use a formula is n over n here. So n, where n is the expected number of particles, and then small n is the number of particles successfully reconstructed. So we look at, by using the control examples, we look at the tracking efficiencies for different versus pt, cosine theta, and phi for different type of particles. So actually they all looks good. Then for PID, we get the similar. We get the particle identification efficiency using control examples for different particles. We efficiency versus P momentum, cosine theta, and phi. So then I will say a few things about reconstruction in EMC. So because EMC reconstruction is a very important the workflow. Firstly, it converts the low ADC values from crystals into the physical energy units, and then do the calibrations. Then there are clustering algorithms will group crystals and with significant energy deposits into clusters, and then when this kind of clustering will be performed in barrel and cap, also in the transition region. And when we do this clustering, and then we will do shower reconstruction, determine the shower shape and the position, and we will refine the energy, and by applying some corrections. So this is a figure shows how to do the what a cluster looks like. That this is energy, because this deposited energy is big, so there's a peak here, and clustering is just to identify these crystals. Then we also, if two cluster the close very close, then we will do cluster splitting according to some criteria. So we will split in there. Firstly, we will identify two seeds, and then split do the cluster splitting. So then after reconstruction, we will do the energy corrections, because why we need to do the energy corrections? Because there are gaps between crystals. So then this correction actually address these kind of issues. And we also will correct the energy loss in the time of flight, compensate the partial energy absorption in the TOF detectors. And we will also do this what we call the absolute energy corrections, ensures accurate conversion of measured signals into true shower energy using some calibration constants from benchmark physics process. So this is an example of shower position corrections. So because the positions actually, this position correction is applied to account for this kind of systematic shifts in reconstructed polar azimuthal angles. So this is a before corrections. This is the expected theta and the reconstructed theta. You see this kind of pattern after correction it disappears. Very good linearity between the reconstructed and the expected value. Then we look at the performance for the resolution. What we got is for Baikal we have for Data 2.3, and for Monte Carlo 2.3, very close, 2.2, and for NCAP a little bit worse. This is the figures are from using Baba events. We use diphotons is a bit worse, but the very good consistency between Monte Carlo and Data. So I will give you the summary of the detector performance of BESIII. You see here we got the spatial resolution about 115 micron for MDC, and DDX is less than 5%, and MEMC resolution 2.4. Compared with other experiments, they are all very close. So for TOF, actually BESIII did a very good job. So actually the resolution is higher than other experiments. So for MUC, the efficiency is relatively high, 96%. Right, so this is the previous or the current experiment, which is still in operation. So how about the future? So future, we have a CPC project, and CPC was proposed by Chinese HAP communities in 2012, and then this has been used to produce Higgs, W, Z, and top, and we will do very precise measurements of Higgs, and also we'll do lots of studies by using this machine. So this is 100 kilometers. The ring length is 100 kilometers. So there are two interaction points. So now we are only working on the detectors for one interaction point. So at the moment, the accelerator design and technology R&D has approaching maturity. So because we already published for the accelerator, published TDR, and also now they are working on EDR, engineering design report. So for detector, so TDR will be ready within this year. So we are working very busy on this project now. So for CPC detector, it's also very similar to BESIII, but there are still key components have been changed, right? So the most inside is the vertex detectors, then it's a silicon detectors, then inner silicon detectors and outer silicon detectors. And also we have a crystal bar ECAL and the glass scintillator HCAL, and most outside is a muon detector. So the physical requirements for tracking the nearly 100%. Momentum resolution also very requirement is very strict, 0.1%. And for particle identification, 2 sigma separations, I think. And then for boson mass resolution is better than 4%. So then for this experiment, we developed a new software, CPC software. It's based on Key4HAP. And we developed the core software using Gaudi as an underlying framework. I will skip this part. Then what I want to talk about is how to do the tracking for this kind of future experiment, because its environment and also detector are completely different. So when we discuss these problems, issues, firstly we look at the backgrounds of the current situations. So now actually the trend in computing hardware is shifting toward increase the number of CPU cores. We have more cores, and also the architecture, hardware architecture is more diverse. So we have GPU, FPGA, and other different kinds of accelerators. And another thing is machine learning has become essential component for high-energy physics experiment. So then this is the background. Then there are a project called ACTS. Is a common tracking software, aims to develop a common track reconstruction software for HAP experiments. So it is designed as a library, just like a Jiangfu. It consists of lots of components. These components can be used to develop your own tracking algorithms. And also there are TrackCC projects. It is a sub-project, actually a sub-project of ACTS. It provides high-performance parallel software compatible with a complex hardware architecture like CPU, GPU, and FPGA. And also there's a TrackX plugin. This also is already there are posters about GNN. This lots of machine learning models has been implemented by this project. So how to do the track reconstruction if we use the ACTS as a library? So just like Jiangfu. So then we just look at how to do tracking in ACTS. So the first step is a space point formation, which also called clustering. So in this tracking detector space points, we also called SP, and also called measurements, actually represents three-dimensional positions in the detectors. And this actually will combine the hits on a detector layer, and then we call it clustering, and then transfer for local measurements into global coordinates, and we get these kind of three-dimensional positions. Before the tracking and stars, actually we also apply like geometry alignment corrections to these space points. So then for the track findings, the first step is the track seeding. So the seeding actually is a process to identify the initial track candidate. We call seeds. It consists of 3 space points. So ACTS actually forms seeds by combining 3 space points. So the 3 space points we also call triplet. So the triplet formation actually is formed by selecting the middle space point, then search the compatible space points in the inner and outer layers. So then when we look at a bit details about this seeding, actually when they do this kind of searching, it will apply cuts in theta and also z, do this kind of cuts to firstly to form the doublets. Then the middle, the top and the bottom doublets will be tested, 2 doublets, and then form the triplets. So by using some criteria. So this is not so complicated. So after that, we'll do track finding and fitting. So the combinatorial Kalman filter, because there are lots of combinations, so we call CKF, combines track finding and track fitting into a single unified process. For the BESIII experiment, actually separated into 2 steps, one the track finding, another track fitting. So for the ACTS, this is one process. So the input to this algorithm actually starts with the track seed already mentioned. So the track seed will give an initial estimation of the track parameters, actually the 3 measurements. And then we are using a Kalman filter method. We'll do the prediction. It will propagate the track state through the detector geometries using ACTS stepper and propagator tools. And then it will search the measurement in the layer, the new layer surface, and we'll try to find the compatible measurements. If measurements is found, new measurements is found, and we'll do branching and the filtering and smoothing, and the propagation will stop when the maximum path length is reached or some customer conditions are met. So all these steps actually using the Kalman filter method. So when further look at the Kalman filter method, so firstly the prediction. So the prediction will predict the state vectors at the next step, k plus 1, based on information at the current step. And then we'll do the filtering. Filtering will filter the predictions of the by incorporating the measurement associated with the step. And then we'll do smoothing. We'll add this x1 step and then do the estimations to refine the track parameters. So I think this method, most of people are already familiar with it. I just go through it because we use it to do the track finding. So then how about the measurement search and the branching? So the search for the detector measurements actually take place at the sensitive surface. And then we evaluate the measurement compatibility based on the predefined criteria, including the number of hits and the chi-square ratio. And for each compatible measurement, actually will spawn a new track candidate branch. So this is how the branch actually produced. Then the final step is called ambiguity solving. So this is the final step. So in the check chain, when the software decides which reconstructed tracks to keep and which to discard, so we'll implement some algorithm to do this job. So this is an example we call greedy solver. So it will discard the worst candidate based on highest fraction of shear hits. And if there is a tile, then the one with the highest chi-square value will be rejected. So after removing this kind of tracks, then the algorithms will recalculate the shear hits and update the ambiguity assessment after proceeding to the next iterations. So this is the final step of a Kalman filter. So for BESIII, for CPC, because in order to meet the demanding requirements of a CPC physics goal, we are using ACTS to do the tracking. Just adopt ACTS for track reconstruction. What we did is firstly we will do the geometry integration. I won't go through the details. And then we will implement the track reconstructions based on the library provided by ACTS. So we build the workflow for CPC experiment, so including seeding, track parameter estimation, track finding, track fitting, and finally to register the track reconstruction results into the Gaudi event store. Before doing this, we need the geometries, materials, and magnetic field. Because this is, we have in our framework, we already implemented the geometry, materials, but for CPC, for ACTS, it has got its own format. So we will prepare this kind of ACTS style geometry and material and magnetic field. And how to do that? I just give you an example. So this is details geometries. Consists of sensitive detectors and passive materials, very complicated. So we're just using Geotino in Jam4, generate many Geotino particles, let it go through the particles, and then we use Jam4 simulation, because Jam4 records the materials transfers by the Geotino. And we recorded it, and for each step we have the radiation length, and we will calculate it, and we will project this material into this layer, do this kind of mapping. So when we also do validations, so we can validate, compare the materials in Jam4 and also the map we get. I think this red, sorry, is too small. Red is from this mapping, and the black spot is from Jam4. So they are consistent with each other very well. Okay, so we have the materials, we have the tracking algorithms. Then we can do the reconstruction. So another thing for silicon detectors is relatively simple, but how about the time projection chamber, TPC? So for TPC, we have some special treatment. So the surface is required by ACTS, actually virtually constructed within TPC gas volume, aligning with the TPC readout layers. I won't go details about this. It's quite complicated. And then then we can apply the ACTS-based reconstruction algorithms to the full simulation data from of the best CPC experiment. So this is the results we get. This is momentum, liquid momentum minus Monte Carlo truth information. So it actually is relatively momentum. So we can see very good distributions, and these are pool distributions. It looks nice. We further check the tracking efficiency. So this is efficiency versus momentum. So it's we got this for low PT tracks actually efficiency drops a little bit. For other higher momentum actually keep a very good tracking efficiency. And this is efficiency versus cosine theta. So actually the drop actually takes place at the large cosine theta area. And this is a small drop here. This is caused by because the geometry, some TPC geometries. So we understand this drop. So maybe we can fix it in the future. Right, so then I come to my conclusion. So I already introduced the how to detect and measure particles produced by high-energy physics collisions, and in order to retrieve this kind of precision measurements and how we developed algorithms. I think algorithms are also very important because high precisions actually the tracking and both tracking and colorimetries actually required sophisticated algorithms to reconstruct these events. And this is I use BESIII as examples. And when the experiment scales up, I also use CPC as examples how we developed reconstruction algorithms for CPC experiments. Okay, thank you very much. Thank you.
Yeah, thank you for your talk. I had two simple questions. The first one, could you provide some numbers about the luminosity of the BESIII and CPC, and how it's comparable to other experiments?
Right. Okay, sorry. I don't have a good memory. Okay. So for CPC, I forgot is 34, something like, yeah, 210. Is that for CPC, right? Yeah.
So it's bigger than on LHC?
Yeah, sure.
Oh, okay.
Sure. Because for CPC is a precision measurement, so luminosity is very important because we will produce lots of Higgs events, so we need a higher luminosity. So.
Thank you, it's very cool.
Any other questions? Thank you for your question. I'd like to ask a question about X. So you mentioned that in X there are common filter for track fitting.
Yeah.
So are there any other algorithms implemented in X?
Sorry? Are there any other?
Yes, any other algorithms.
Okay. Oh, yeah, sure. So this here. Because here I already mentioned we are using like CKF Kalman filter to do the track finding, both track finding and track fitting. Because there are some limitation for a Kalman filter, CKF, because it requires the area of measurement is a Gaussian distribution. So this is the requirements. If there are some bias, then we get the track parameters actually is not very good. So, but in the reality, lots of measurements actually is not Gaussian, right? Lots of happens. Probably double Gaussians, several Gaussians. So it's the distributions is very complicated. So how to handle this? So in ACTS, we also have other options. So one method is use GSF. So it's a Gaussian sum filtering. So basically, it has got many Gaussian distributions. So this can fit the data very well. So if we also implement these algorithms and compared with the CKF, so for the ideal situation, the consistent with each other very good. But for some track, for example, electrons, because I already mentioned for electrons, the brainstorm is a very big effects. When the electron pass through the material, it will emit the photons. So then we look at the measurement. Actually, it doesn't abide the Gaussian distributions. So then we use the GSF method to do this kind of track finding and track fitting. Actually, we can get a very good estimation of track.
So for electrons, CKF is very good, and for the other cases, you experiment with the other algorithms?
Yeah, other options, because I forgot to say, this is another area. We can also use machine learning method to do the track finding. But the track fitting, we still need this kind of calculation algorithm to do the track fitting. So the machine learning method only responsible for track finding.
Okay, thank you.
Any other ones? Okay, if no, let's thanks Professor Lee again.
Okay, thank you. Thank you.